previously we talked about first order low pass and high pass filter characteristics. In this hour we'll be talking about the characteristics of a band pass filter. To realize which you need at least a second order circuit. Okay, so the general form that we will consider can be represented by the following transfer function. Okay, h of s equals ks. So we have a 0 at the origin and two poles for our transfer function. Okay. In order to be able to talk about a filter, we should be able to talk about a steady state, and for a steady state to exist, the circuit should be stable. So that means the poles should be with negative real parts. So that means alpha and omega 0 in our prototype are positive real numbers. Okay, so omega 0 positive and alpha is also positive. This guy omega 0 is called the center frequency and alpha is called the damping factor. Okay, now let's, for this prototype, second order band pass filter, let's try to figure out the gain and phase characteristics. Okay, so we can write the following: h j omega equals k j omega, and then we have minus j omega square, which produces minus omega square, plus 2 alpha omega 0 j omega plus omega 0 square. Okay, now let's reorganize this expression so that it becomes easier for us to see certain things. First, allow me to write the following: k j omega omega 0 multiplying 2 alpha plus omega 0 over j omega minus omega over j omega 0. Okay, and then these j omegas, they cancel one another, and we're left with the following expression: k over omega 0 in the numerator, and the denominator can be written in the following simple form: 2 alpha plus j omega over omega 0 minus omega 0 over omega. Okay, now starting from this, now let's talk about gain and phase characteristics. We begin with the gain function. Okay, h j omega magnitude. So that equals the magnitude of the numerator divided by the magnitude of the denominator. Note that we didn't make any assumptions on the sign of k, so it's a real number, but it could be either positive or negative. So what we do is we write for the numerator the absolute value of k over omega 0. As for the denominator, which is a complex number, the magnitude is 2 alpha square plus omega 0 minus omega 0 over omega square, and then we take the square root, 1/2. Okay, so that's our gain function. So let's try to figure out qualitatively what kind of shape that we expect from that function of omega. Okay, namely the magnitude of h omega versus the frequency omega. Let's begin by figuring out the maximum value that the gain function can achieve. So the numerator is fixed. Okay, the only thing that depends on the frequency is the denominator. In fact, this part of the denominator. Okay. So, since this is never a negative number, this is always non-negative. So, the whole thing, the gain is maximum when the denominator is minimum. Okay, and the denominator is minimum when this guy is minimum and this guy is never negative. Therefore, the minimum value that it can achieve, if it can achieve it, is 0. So let's see whether 0 can be achieved by this term or not. Incidentally, well, as a matter of fact, 0 can be achieved if you plug in omega equals omega 0. What you have is omega 0 over omega 0, 1, omega 0 over omega 0, another 1, 1 minus 1, 0. Therefore, this term can be made 0. Okay, when this term is made 0 by picking omega equals omega 0, so what remains is numerator divided by 2 alpha square root, so that's 2 alpha. Hence, the maximum value of the gain, which is clear from this expression, is magnitude of k divided by 2 alpha omega 0. Okay, so let's put that observation down. Hg omega max is achieved at hj omega 0. Okay, achieved at omega equals omega 0, and that equals, okay, once again at omega equals omega 0, this term here disappears, and what we have is this divided by 2 alpha square, and then the square root is taken, so that makes 2 alpha. Okay, 2 alpha omega 0. So that's the maximum gain we can achieve with our filter, whose transfer function is given here. Okay. Now let's try to qualitatively figure out what happens, okay, at low frequencies, and also what happens at high frequencies. Okay. So at low frequencies, and by low frequencies, it makes sense to consider the frequencies that are significantly smaller than omega 0. So that omega 0 is important from that point of view. That's why we're calling it the center frequency. Okay. So at low frequencies, by which we mean omega significantly smaller than the filter parameter omega 0, let's figure out what the gain does qualitatively, and also let's do the same thing for high frequencies. At high frequencies, and not surprisingly, by high frequencies, it makes sense to consider the frequencies that are significantly larger than omega 0. Note that omega 0 is the frequency where the maximum is achieved. Okay. Hj omega. Let's figure out where this function tends to at low and high frequencies. Now, suppose that omega is significantly smaller than omega 0, and this is our gain function. If omega is significantly smaller than omega 0, okay, let's say, or for simplicity, let's consider omega near 0. Okay, if omega is very small, then this thing is very large, this term here, okay? Omega 0 over omega. So it will dominate the denominator. And if this thing is very large, therefore we can approximate the denominator with omega 0 over omega, okay? And then at omega, when omega is very small, this thing is very large. And if this thing is very large, since it appears in the denominator, the whole thing is very small. So that means at low frequencies, the gain is close to 0. Okay, so the gain tends to 0. Now what happens at high frequencies? When omega is significantly larger than omega 0, this time, this is the dominating term, okay? Omega is very large, so we can forget about the remaining two terms in the denominator. If this thing is very large, then since it appears in the denominator, the overall thing is very small. So that's, we see once again that at very high frequencies, the gain tends to 0 once again, okay? Okay. Okay. So what we have therefore observed qualitatively is that at some frequency, which we call the center frequency, which is omega 0, our gain function, our filter, achieves the maximum value that it can get. At frequencies significantly to the left of that frequency, okay, frequencies smaller than omega 0, we figured out that the gain is very small. And if you go to the right, again, the gain right of omega 0, again, the gain becomes eventually very small. So that means the overall gain function will have a bump-like shape. It starts around 0 at low frequencies, okay, and then somewhere in the middle, by middle we mean frequencies around omega 0, it achieves something significant, some significant gain, and then as you further increase the frequency, if you go toward right from omega 0, again it starts decreasing and eventually it tends to 0 as omega goes to infinity. So let's summarize that on a plot. Okay, so this is the outcome of our qualitative analysis. Omega versus H omega. Okay. So at low frequencies we are here. At very high frequencies again we're close to 0. So what we expect is something like that as the shape of the gain function. This point, the peak, is achieved at omega 0, okay, and we also figured out the value that the gain attains, okay, that's the max, and that equals the following ratio: 2 alpha omega 0, okay, which is dividing the magnitude of k. Okay, so that's basically the shape of our bandpass filter, and it's clear why it's called a bandpass filter. Okay, it doesn't pass low frequencies to the other side, to the output side. Let's say it doesn't pass much of the input to the output when the frequency is high. And somewhere in between, around the frequency omega 0, we see something that's significant at the output side. That's why this is clearly called a bandpass filter. Okay, now let's figure out the frequencies okay, at which the gain equals max divided by square root of 2. Okay, max divided by square root of 2. Those frequencies, remember, we called the cutoff frequencies, and between the cutoff frequencies we have what we call the bandpass, and anything outside bandpass is what we're calling this pass band, and anything that's outside pass band we're calling the stop band. Okay, so for our filter, therefore, this is part of our stop band, this is the other part of our stop band, and in between we have our pass band. Okay, and here we have pass band. Okay, now the next question we will now answer is what are the cutoff frequencies in terms of the filter parameters, namely k, omega 0 and alpha. let's figure out omega C1 and omega C2. Okay, the definition of those frequencies are clear on the figure. You figure out the maximum value that the gain can achieve, which we did, and then divide that by square root of 2, and the frequencies corresponding to frequencies at which the gain achieves that max over square root of 2 value are what we're calling the cutoff frequencies. And those frequencies, they mark the border between passband and an adjacent stop band. Okay, so Hj omega C by definition equals Hj omega max divided by square root of 2. Okay, so if we apply this definition to our prototype, omega 0 over 4 alpha squared plus omega c over omega 0 minus omega 0 over omega z square 1/2, and that equals max 2 alpha omega 0 times 1 over square root of 2. Okay, now in this equation we're solving for the unknown omega c, the cutoff frequencies. Okay, so we have this and that cancelled, this and that are also cancelled, and then what happens is then the following. So here we have gotten rid of the numerator, so that means the denominator here and the denominator over there must be equal to one another. Okay, and then to get rid of this square rooting operation, let's take the square root of both sides, and here what we have is 4 alpha squared plus omega c over omega 0 minus omega 0 over omega c square, and on the other side what we have is 2 times square root of 2 times alpha. Taking the square of that produces 8 alpha squared. Okay. Taking this guy to the other side produces 4 alpha squared, which we can write as 2 alpha square equals omega c over omega 0 minus omega 0 over omega c squared. Okay, because we have an omega c here in the denominator and we have a square here, so this is a 4th order equation, so it will have 4 roots, but we're not interested in the negative roots because we're looking for a frequency, and by definition frequency is positive. Okay, therefore that equation will produce 2 numbers, and those 2 numbers will be our cutoff frequencies. It's not difficult to check that. Let's call this equation 1. That equation is solved by the following 2 positive numbers. Omega c1 equals omega 0 1 plus alpha square minus alpha. Okay, so that's one possibility, one positive possibility. The other positive possibility is what we're calling omega c2, and that equals omega 0 1 plus alpha square, this time plus alpha. Okay, so that's, this pair is our cutoff frequency pair. Note that omega c1, omega c2, their product produces the square of the center frequency, omega 0 square. Therefore, the center frequency equals the geometric mean of the cutoff frequencies. Okay. Now, once we have the cutoff frequencies, we can easily figure out the pass band, bandwidth, which is the length of the passband. In this case, is omega c2 minus omega c1, and that produces 2 alpha omega 0. Okay, so let's put that down. the bandwidth of our second order band pass filter is equals omega C2 minus omega C1. Okay, the difference between two cutoff frequencies, and the cutoff frequencies are computed here, and that produces 2 alpha omega 0. Okay, therefore bandwidth has nothing to do with the parameter k, okay, of our filter. And now we're going to introduce a new quantity which we'll be calling the quality factor. Okay, and the quality factor associated to our second order band pass filter is defined as omega 0 over b, the ratio of the center frequency to bandwidth. Okay, and in terms of our filter parameters, b was computed as 2 alpha omega 0. So omega 0 over 2 alpha omega 0, that produces 1 over 2 alpha. So that means lower the damping factor, higher the quality factor. Okay. Okay, so let me put an explanation regarding the quality factor. Quality factor is an indicator of how sharp the peak of the gain response is. Okay, and if Q is larger than unity, such filter is sometimes classified as narrow band filter. Okay, so it's the peak is sharper. Narrow band filter. And the other possibility, when Q is smaller than 1, it's called a broadband filter. Okay. So for now, that's about it regarding what can be said about the gain function. Now let's also try to figure out some qualitative aspects of the phase function, okay, of our second order band pass filter. Okay. Phase. Okay, phase function. Now we have put h omega in the following form, which proved to be helpful when we try to figure out certain properties of the gain function. It will also be helpful when we study the phase properties of our band pass filter. Now h omega had the following form: k over omega 0, and we have 2 alpha plus j omega over omega 0 minus omega 0 over omega. Okay. Now again, we try to see what happens qualitatively, okay, to phase when omega is small or significantly smaller than omega 0, and likewise we're going to consider the other possibility when omega is significantly larger than omega 0. Okay, so let's now discuss what happens to phase at low frequencies and at high frequencies. At low frequencies, by which we mean omega significantly smaller than omega 0. Let's figure out what happens to the phase function theta omega, and also at at high frequencies, we will try to figure out what happens to the theta omega. Okay, let's begin by what happens at low frequencies. At low frequencies, that is when omega is significantly smaller than omega 0. So that means omega 0 over omega, this term, is much larger than the remaining terms in the denominator. So that means at low frequencies, our H omega, our transfer function, has the following form: approximately k over omega 0 and divided by minus j omega 0 over omega. Okay. So that's approximately what H omega is at low frequencies, because at low frequencies this is the dominating term in the denominator. Now, since we're interested in the phase of this is k, the phase of the numerator minus the phase of denominator. Phase of the numerator, since omega 0 is positive, equals the phase of k. If k is positive, if it's a positive real number, then the phase of the numerator is 0. Otherwise, it's 180 degrees. Okay, but in any case, the phase of this guy is phase of k minus phase of the denominator. Now, in this case, the phase of denominator is minus 90 degrees. Therefore, minus 90 degrees, that produces the phase of numerator plus 90 degrees approximately when the frequency is low. Okay, so therefore theta tends to the phase of k plus 90 degrees at low frequencies. Now let's see what happens at high frequencies. Now when omega is significantly larger than omega 0, in that case this term here is the dominating term in the denominator. So that means H omega can be approximated by plus j omega over omega 0. Okay. And as for the numerator is k over omega 0. This time the phase equals, well, again, it equals the phase of numerator minus phase of denominator. But this time the phase of the denominator is 90 degrees. Therefore, what we have as the overall phase of k minus 90 degrees. Okay, when the frequency is high, minus 90 degrees, and phase of k is 0 if it's a positive number. Otherwise, it introduces a phase of pi radians or 180 degrees if it's negative. Okay, for k negative. Now, let's therefore obtain the phase plot roughly following our qualitative analysis. So the phase hence will look like this. Okay, suppose that we're working with a negative k. Okay, so the phase of it is therefore 180 degrees. So at low frequencies, what we have is the phase of k, which is 180 degrees, plus 90 degrees. So that means 270 degrees. So we start around 270 degrees. Okay. Okay, let's say this is 270. 270 degrees. Okay. And at very high frequencies, we tend to, this is 180 degrees, 180 minus 90 degrees, so we are tending to 90 degrees, okay, 90 degrees. And this is 180 degrees. Okay, so the shape of the phase plot, therefore, will look approximately like this. Okay. And what happens, let's see, at the center frequency when omega equals omega 0, this is 1, this is also 1, 1 minus 1, 0. Therefore, at center frequency, numerator becomes purely real, and 2 alpha was positive. Therefore, the phase of the numerator is 0. That means at the center frequency, the phase of the transfer function or phase of our filter equals the phase of k. And in our example, k was negative, so that produces 180 degrees. Okay, omega 0. If k were positive, then at the center frequency, the phase of h omega is simply 0. Okay, now let's see a circuit where we can, a circuit that produces a second order bandpass characteristics. Okay, so that's our example. Okay, this is our circuit directly given in S domain. The voltage provided by the independent voltage source is our input. Okay, the impedance of the inductor is SL, the impedance of the capacitor is 1 over SC, and we have the resistor with resistance R. So this is the input voltage, and where we collect the output is we collect it as voltage that appears across the terms of the resistor. Namely, this is our output voltage. Okay. So the transfer function is very easy to compute in this case. Okay, by V out of S divided by V in of S, which by simple voltage division equals to R over the overall impedance, okay, seen by the source, the input voltage. Okay, so that means H of S equals R over the input impedance, SL plus 1 over SC plus R, which can be written as R over LS S squared plus R over LS plus 1 over LC. Okay, so remember the prototype of a second order bandpass filter that we studied. It had the following form: Ks over S squared plus 2 alpha omega 0 S plus omega 0 squared. Okay, so that means, first of all, the transfer function fits to our prototype. Therefore, this indeed is a second order bandpass filter. Okay, with K being equal to R over L, omega 0 being equal to 1 over square root of LC, and then alpha is R over L divided by 2 omega 0. Okay, so let's express those parameters in terms of our circuit parameters. Okay, so our circuit produces the following coefficients. K is R over L, the center frequency equals 1 over square root of LC, which, observe, is independent of the resistance value. It only depends on the inductance and the capacitance. Okay, and then 2 alpha omega 0 also equals R over L, from which we can pull alpha to omega 0 L, which equals omega 0 being 1 over square root of LC, R over 2 square root of C over L. Okay. What's the maximum gain that we can achieve with our filter? Let's compute that. Hj omega max equals 2 alpha omega 0, and maximum is achieved at omega equals omega 0. So in this case, the maximum gain that we can obtain from our filter occurs at frequency equals 1 over square root of LC. Now K and 2 alpha omega 0, they're the same, R over L, therefore the maximum gain that we can achieve is unity, okay, 1. And how about the bandwidth? Bandwidth is 2 alpha omega 0. This is the difference between two cutoff frequencies, and that equals, in terms of our circuit parameters, R over L. And finally, let's also compute the quality factor, the latest parameter that we introduced. Q, by definition, equals the center frequency divided by the bandwidth over 1 over 2 alpha, and that for our circuit equals 1 over R divided by multiplying square root of L over C. Okay. Now let's try to append a physical meaning to the quality factor for this circuit. Okay. Physical meaning, if it exists, of Q. Okay, remember that for our circuit, this is what we computed, okay, to equal Q. Okay, now let's consider the circuit at the very center frequency, at omega 0, okay. Okay, this is R, this is the in, here omega 0, L is the impedance of our inductor at frequency omega 0. So what we're doing is we're considering the circuit at omega equals omega 0. Consider the circuit at omega equals omega 0. So that means we're driving the circuit with an input whose frequency, a sinusoidal signal whose frequency equals 1 over square root of LC. Okay, so V in T, in time domain, the voltage equals A, some amplitude times cosine omega 0 plus some phase. Okay, and omega 0 for our circuit equals 1 over square root of LC. Okay, so this is the impedance of the inductor at that frequency. Likewise, we have 1 over J omega 0 C, so that's the impedance of our capacitor. And this is the phasor of the current that flows in the circuit at that particular frequency. Okay, now let's compute total stored energy at this particular frequency in our circuit. Okay, total average stored energy. Let's call it ES. So we have two energy storing elements in our circuit, the inductor and the capacitor. Therefore, by total average stored energy, we mean total average stored energy in the inductor plus the average stored energy in the inductor plus the average stored energy in the capacitor. Okay, so ES therefore equals EL plus EC. Average stored energy in the inductor plus average stored energy in the capacitor. Okay, so let's compute those quantities, EL, EC, and then finally ES. So what's EL? EL is 1/2 times the inductance times the square of the effective value of the current passing through the inductor. I effective square. And the average stored energy in the capacitor can be computed using the dual formula, 1/2 times capacitance times the effective value of the voltage that appears across the terminals of the capacitor. Okay, so 1/2 times C times V C effective square. But now let's express everything in terms of the current. Therefore, the effective value of the voltage of the capacitor simply is the magnitude of the impedance of the capacitor times the effective value of the current passing through the capacitor. Therefore, what we have is I effective times the magnitude of the impedance, which is 1/ω0/C. So that produces V effective, and then we're squaring it to figure out the energy. Okay. Therefore, this plus that produces the total stored energy. Now, what's ω0? ω0 equals 1/square of LC. And when ω0 is replaced by this term here, we see that at the center frequency, stored energy in the inductor equals the stored energy in the capacitor. Okay, so ES, total stored energy, therefore equals 1/2 Li effective square plus 1/2 Ci effective square times square root of LC over C square. Okay, and this is coming from the ω0 in the denominator, and that equals Li effective square. Okay, so that's the stored energy. Let's also now compute the energy dissipated on the resistor in one cycle. Okay, and then when we compare those two energies, we're going to see that ratio is very close related to what we're calling the quality factor. Okay. Energy dissipated on the resistor during one period. Okay, let's call that energy ED, dissipated energy on the resistor. So that equals, you take the average power absorbed by the resistor and then multiply that by the period, okay? T. That equals R times I effective square, and period is 1/f, and f is what? ω0 over 2 pi, and ω0 is 1/square root of LC. Therefore, we can write Ri effective times 2 pi over ω0, and that's 2 pi I effective square times R square root of LC. Okay. Now, we make the following very interesting observation through which we can talk about the physical meaning of the quality factor. Observe that ES over ED, that is the ratio of the total average stored energy in the circuit to the energy dissipated on the resistor during one cycle, during one period, equals Li effective square over 2 pi I effective square times R times square root of LC. Okay, that equals 1 over 2 pi times 1 over R dividing square root of L over C. And this thing was our quality factor. So therefore that equals the quality factor over 2 pi. Okay. Therefore what we have obtained is that quality factor is proportional to average stored energy in the circuit divided by energy dissipated in one cycle. Okay, and the proportionality constant happens to be 2 pi. Okay, therefore Q equals 2 pi times this ratio. Okay, which produces a very meaningful answer to our question.